So again, chapter 19, I want to finish up with two kind of finer points on this. One is the relationship between free energy and pressure. So please remember G is Gibbs free energy, Gibbs free energy. And again, free energy is available to do work, okay, available to do work. So under constant temperature and pressure, the reaction will always go in the direction to lower free energy to get that negative delta G. Well, what is the only thing that does work in chemistry? And that is gases, okay? What is gases affected by? Pressure and temperature. So if I have a different pressure and a different temperature than 25 degrees Celsius and 1 atmosphere, I'm going to have a different delta G. So to kind of just summarize this, and I'll show you how to do the calculation. If I have a gas in a container and I'm looking at pressure and volume, the larger the volume, the more S you're going to have, or the larger the entropy is going to be compared to the small volume. So here's a large volume, here's a small volume. If I have 4 particles in there, okay, you will see that in the larger box that I have more ability to move these 4 particles around and disorder them, versus in a smaller container there's less likelihood of me to get that. At low pressure is going to be due to the fact that I have a large volume. Okay, so if I'm in a low pressure situation, these particles can move wherever they want and have more chaos. If we have high pressure, they're bouncing off each other and they don't really have much place to go. So that is why we will say that this is much more ordered in terms of how close those particles get together versus low pressure where they're a little bit more spread out. So we have this equation here, okay, that you're not really going to have to know for my test or the AP test, but I like to just introduce it so you could see that if you're not at standard conditions, there is another way of looking at these types of calculations. So delta G without a degree sign, so please recognize that this does not have a degree sign, but this does. So delta G degree sign have been how we've been calculating all of these. But what if I had it at a different temperature and a different pressure? So then I'm going to have this part of the equation to kind of include RT ln of Q, and that is because we're going back to PV equals nRT. Now there's a way to derive this. I'm not going to spend the time talking about that. But the R we're going to use here is a joule Kelvin mole one, which is the 8.314. So let me show you the calculation. You can kind of see where it goes in terms of understanding, and then we'll move on to the last topic. So delta G at 25 degrees Celsius with 2 atmospheres of ammonia, 3 atmospheres of oxygen, 2.4 atmospheres of N2O, and 1.8 atmospheres of water. So I've been given the delta G of formation of all of these substances, and please recognize oxygen is 0 because that's an element. So all I got to do is find my delta G of my reaction, okay, at standard conditions. It's going to be products minus reactants. Well, it comes out to be negative 549 kilojoules. So I'm going to plug that into this new equation. So delta G at standard conditions plus RT ln of Q. So I have to find my Q. So Q again is going to be products over reactants. Okay, so going back to our equilibrium days. So 2.4, 1.8, and there are 3 water molecules, so I got to cube that. 2 squared, 3 squared. Q comes out to be 0.3888. So then to find my delta G under non-standard conditions, negative 549 kilojoules, plus my R is 8.314. Recognize this is joule Kelvin mole. Okay, I got 298 as my Kelvin, and then it's the natural log of 0.3888. So recognize this is in joules, so really I need to convert this to joules first, or convert this to kilojoules and just make sure everything is the same. Regardless, this comes out to be negative 551 kilojoules of my free energy. So you will see that the free energy essentially went from 549 kilojoules to 551. So it does go up a little bit, and that is because, again, you're going from 4 moles, 4 moles to 4 moles. So you do have some increase possibly due to, again, maybe more complex molecules over here, but really these kinds of calculations you're not going to be focusing on for me or the AP test. But I still like to show it just so you have some reference as to if we're not at the right, if we're not under standard conditions. But what you do need to know is the relationship between G and equilibrium, okay? So the key is always to get to negative delta G. That's one thing you remember about this chapter is you want delta G to be negative. You want delta G to be negative. So at equilibrium, Q is equal to K. My change in delta G at equilibrium will equal to 0. So these are statements that we've already seen. These are statements we've already seen. So if I go back to this equation here that I just showed you, my overall delta G is going to be due to standard conditions plus RT ln of Q. Well, if my delta G at equilibrium is 0, my reaction plus RT is the ln of K. So essentially what I'm doing is deriving this next equation. So this equation is on your formula sheet. Okay, so you will need to know this one, and we will be using this one. Okay, formula sheet. So delta G under standard conditions is 0. The system is at equilibrium. Well, that must mean K is equal to 1. Okay, because if K is equal to 1, ln of 1 is 0. So the delta G comes out to be 0. If my K is greater than 1, it will keep everything here to be a negative, so your delta G is going to be below 0. And if K is less than 1, then your delta G is going to be positive. Well, that should make sense, because if K is products over reactants, okay, that means I am favoring the right. I am favoring products. So yes, it is spontaneous the way it is written. And yes, I get that negative delta G. Well, if my K is less than 1, that means reactants are favored. This is where I feel it all comes together. So the reactants are favored. So that means no, it is not considered to be spontaneous, and your delta G turns out to be positive. Okay. So that's why this equation is so very helpful. And the reason I showed you the other equation was just to get to this one. Okay, so this is the one that you need to know. So if I'm giving you an equation like this, find the K for this reaction if I give you the delta H and the S. Okay, so what I gotta find first is the delta H of the overall reaction. So that's gonna be products minus reactants. Well, it comes out to be about 58 kilojoules. Again, so N2 times 2 minus 10 gives me 58 kilojoules. My S, again, please recognize that on my notes I do everything in joules. So this is 304 and this is 240. So the delta S of that reaction comes out to be 176 joules per Kelvin. So my delta G with a degree sign is equal to, I'm going to convert this to joules, by the way. So 58,000 joules minus my 298 Kelvin times my 176 joules per Kelvin. So Kelvins cancel, and I'm all in joules. I'm all in joules. So it comes out to be 5,552 joules, which is a positive delta G. Okay, that makes sense. So my K I know is going to be less than 1. I know my K is going to be less than 1. So how do I solve essentially for K? So I'm going to have to bring The R and the T to be below, so KEQ is going to have to be E to the negative delta G over RT. Okay, so I divided RT negative over here, so this becomes negative. And if you bring the natural log over here, it becomes E. So if you go to your calculator, you will see E is above the natural log key. So in this case, it becomes negative 5552 joules over 8.314 times 298 Kelvin. So please recognize I kept the G in joules because I knew the R I was going to use was 8.314, and that's in joules as well. So just keep it in mind in terms of how you're setting this up. So plug that in your calculator, and you should get 0.106 as your K value, Again, this is going to be the equation you focus on. Don't worry about non-standard conditions. I'm not going to focus on that. Instead, you need to know what's the relationship between delta G and K.